The base model is a design philosophy for managing data in distributed systems, primarily used in NoSQL databases. It stands for B. Basically available. A. Soft state. S. Eventually consistent. For more tech interview materials, please go to our website at bowz8.com. Breaking down the base components. 1. Basically available. Meaning, the system ensures that data is available, even if parts of the system fail. Practical application. Instead of blocking operations until the entire system achieves consistency, the system responds to requests with whatever data is available at that moment. Example: in a distributed cache system like Redis, if one node fails, other nodes can still serve data, ensuring availability. 2. Soft state. Meaning, the system allows the state to change over time, even without new input. Why this matters? Because updates may not be instantaneously synchronized across nodes. The system can tolerate temporary inconsistencies. Example: in a social media application, your post may appear in your feed immediately, but it might take some time to appear in your friend's feed due to replication delays. 3. Eventually consistent. Meaning, while the system does not guarantee immediate consistency, it guarantees that all replicas will converge to the same state eventually. How it works: background processes or synchronization mechanisms update the nodes over time. Example: in systems like Amazon DynamoDB, data updates propagate across nodes asynchronously, ensuring eventual consistency. ACID guarantees immediate consistency, making it ideal for banking, financial transactions, and other critical operations. Base prioritizes availability and performance, making it ideal for large-scale applications like social media, e-commerce, and real-time analytics. How Base achieves high availability. 1. Replication. Data is copied across multiple nodes to ensure redundancy. If one node fails, other nodes can still respond to requests. Example: in a distributed database like Cassandra, data is replicated to multiple nodes, so data remains available even if some nodes fail. 2. Sharding. Data is split into smaller chunks, shards, and distributed across multiple servers. This improves scalability and allows systems to handle more requests. Example: MongoDB uses Sharding to distribute large datasets. 3. Eventual consistency mechanisms. Anti-entropy. Background processes sync data across nodes periodically. Read repair. When a node detects stale data during a read, it triggers an update to bring the data in sync. Gossip protocols. Nodes share updates with each other periodically to propagate changes. Common base implementations. 1. Apache Cassandra. A highly scalable, distributed NoSQL database that ensures high availability and eventual consistency through replication and partitioning. 2. Amazon DynamoDB. A managed NoSQL database designed for low latency and scalability, offering eventual consistency with strong consistency options. 3. MongoDB. A document-oriented database that supports sharding and replication with the option for eventual consistency. 4. Redis. An in-memory key-value store that can be used for caching, message brokering, and real-time data with eventual consistency options. Benefits of Base are: 1. Scalability. Easier to scale horizontally by adding more servers to the system. 2. Fault tolerance. Ensures the system continues to function even during node failures. 3. Performance. High availability and low latency reads/writes due to relaxed consistency requirements. 4. Flexibility. Suitable for applications where some level of temporary inconsistency is acceptable. Drawbacks of Base include: 1. Inconsistent data. Temporary inconsistencies may be problematic for applications needing strict consistency. 2. Complex development. Developers need to handle inconsistency and reconciliation logic in the application layer. 3. Limited transactions. Full ACID transactions are often not supported, making it unsuitable for applications requiring atomicity and isolation. Thanks for watching. For more tech interview materials, please go to our website at bowz8.com. Data sharding is a method used to divide a large dataset into smaller, more manageable pieces called shards and distribute these shards across multiple servers or nodes within a distributed system. This strategy helps improve performance, scalability, and manageability of data-intensive applications. For more tech interview materials, please go to our website at bowsy8.com. How data sharding works. 1. Splitting the data. The system divides a large dataset into multiple shards based on a shard key. For instance, a dataset of user accounts could be split based on user ID. Shard 1, user ID 1 to 1000. Shard 2, user ID 1001 to 2000. 2. Distributing the shards. Each shard is assigned to a different node in the cluster. This allows the workload to be evenly spread out, improving system performance. 3. Querying data. When a query comes in, the system uses the shard key to determine which shard holds the relevant data. This avoids scanning the entire dataset, making queries faster. 4. Rebalancing shards. As data grows, some shards may become larger than others, hotspots. Rebalancing involves redistributing data to ensure all shards remain manageable. Benefits of sharding include 1. Scalability. Distributes data and workload across multiple nodes, allowing the system to handle large datasets and high traffic. 2. Performance improvement. Since each node handles only a fraction of the total data, queries are faster and write operations are less burdensome. 3. Manageability. Smaller, distributed datasets are easier to maintain, backup, and restore. 4. Fault tolerance. If one shard or node fails, only a portion of the data is affected. Challenges in sharding include 1. Shard key selection. A poor shard key can lead to uneven data distribution, hotspots. Example, if using country as a shard key, one country with many users could overload a single shard. 2. Cross-shard queries. Queries that require data from multiple shards, e.g. aggregations, are slower and more complex. 3. Rebalancing. As data grows, redistributing shards can be challenging and resource-intensive. 4. Complexity. Implementing and maintaining a sharded system adds complexity to application logic and database management. Thanks for watching. For more tech interview materials, please go to our website at bowsy8.com. In a distributed system, data replication ensures that multiple copies of the same data are stored across different nodes or servers. This improves fault tolerance, availability, and sometimes performance. Here's a concise breakdown of how it works, including key concepts, replication types, and challenges. For more tech interview materials, please go to our website at bowsy8.com. Major types of data replication are 1. Synchronous replication. When data is written to the primary node, the system waits until all replicas confirm the write before acknowledging success. Advantages. Strong consistency. All nodes have the same data. Disadvantages. Slower performance due to waiting for all confirmations. If a replica is slow or unavailable, the write operation can be delayed. Use case. Financial systems requiring strong consistency. 2. Asynchronous replication. The primary node processes the write and immediately acknowledges success, while replicas are updated in the background. Advantages. Faster writes and improved system performance. Disadvantages. Temporary inconsistencies between replicas, eventual consistency. Use case. Social media platforms or large-scale web applications where availability is more critical than immediate consistency. 3. Leader-follower replication. Master-slave. A leader node handles all write operations. Follower nodes replicate data from the leader and handle read operations. Advantages. Simplifies conflict resolution and supports read scaling. Disadvantages. If the leader fails, a new leader must be elected. Downtime. 4. Multi-leader replication. Master-master. Multiple nodes can accept write operations. Synchronization occurs between leaders. Advantages. High availability and fault tolerance. Disadvantages. More complex conflict resolution. 5. Peer-to-peer replication. All nodes are equal and can handle both reads and writes. Advantages. No single point of failure. Disadvantages. Complex synchronization and consistency management. Replication mechanisms. 1. Log-based replication. Changes are recorded in a transaction log and replayed on replicas. 2. Snapshot replication. Periodic snapshots of the database state are replicated to other nodes. 3. Gossip protocol. Nodes exchange data updates by gossiping with each other, gradually propagating changes throughout the system. Benefits of data replication are 1. High availability. If one node fails, another node with the replica can still serve requests. 2. Fault tolerance. Reduces the risk of data loss by maintaining redundant copies. 3. Improved performance. Read scaling. Distributes read operations across replicas to balance load. Geographic distribution. Data can be replicated to regions closer to users for faster access. Challenges in data replication include 1. Consistency. Ensuring all replicas are up to date, especially in asynchronous replication. 2. Latency. Synchronous replication can introduce delays. 3. Network partitioning. Handling network splits and reconciling diverging data. 4. Conflict resolution. In multi-leader systems, concurrent writes may cause conflicts that need resolution. Thanks for watching. For more tech interview materials, please go to our website at bowsy8.com.
Virtualization is a technology that allows you to create multiple simulated environments or virtual resources, such as servers, desktops, storage, and networks, from a single physical system. It's a core concept behind cloud computing, optimizing hardware utilization and enabling flexibility in IT infrastructure. For more tech interview materials, please go to our website at bowsy8.com. At its core, virtualization abstracts physical hardware and creates virtual versions of resources. Instead of dedicating a single server to one task, virtualization lets you run multiple virtual machines, VMs, on a single physical server. Virtualization is managed by a software component called a hypervisor. A hypervisor is a layer of software that allows multiple VMs to run on a single physical machine by distributing hardware resources, CPU, memory, disk, etc., among them. There are two main types of hypervisors. Type 1 hypervisor, bare metal, runs directly on physical hardware. Examples: VMware ESG, Microsoft Hyper-V, Xen. Used in enterprise data centers for better performance and security. 2. Type 2 hypervisor, hosted, runs on top of a host operating system. Examples: VMware Workstation, Oracle VirtualBox. Used in personal and development environments. How hypervisor allocates resources. Hardware virtualization. The hypervisor maps physical hardware, CPU, RAM, storage, network interfaces to each VM, ensuring that they can operate independently. Isolation. VMs are isolated from one another, meaning if one crashes or has a security issue, it doesn't affect the others. Components of virtualization include 1. Host machine. The physical server running the hypervisor. 2. Guest OS. Each VM runs its own guest operating system, Windows, Linux, etc. 3. Virtual hardware. Each VM has virtualized versions of hardware components, e.g., virtual CPU, virtual RAM, virtual disk. 4. VM images. Pre-configured templates that can be quickly deployed as new VMs. Virtualization types. 1. Server virtualization. Multiple server instances run on a single physical server. Improves hardware utilization and reduces costs. 2. Desktop virtualization. Virtual desktops run on a centralized server. Used in virtual desktop infrastructure, VDI, solutions. 3. Network virtualization. Combines network resources into a single, software-based virtual network. Examples: SDN, software-defined networking. 4. Storage virtualization. Pools storage from multiple devices into a unified system. Benefits of virtualization include 1. Resource efficiency. Maximizes the use of hardware by running multiple VMs on a single server. 2. Scalability. Easily add new VMs without purchasing additional hardware. 3. Flexibility. Quickly provision or migrate VMs across servers. 4. Cost savings. Reduces hardware and energy costs. 5. Isolation. Each VM runs independently, improving security and stability. Thanks for watching. For more tech interview materials, please go to our website at bowz8.com. Containerization is a lightweight, efficient method for packaging, deploying, and running applications. It allows software to run reliably across different computing environments. Unlike traditional virtualization, containers share the host system's OS kernel, making them faster and more resource efficient. For more tech interview materials, please go to our website at bowz8.com. A container is a standardized unit of software that packages an application and its dependencies, libraries, binaries, configuration files, together. How containerization works. 1. Container image. A container image is a read-only template that defines how the container should run. Includes the application code, dependencies, libraries, and settings. 2. Container engine. Software like Docker or Podman manages and runs containers. The engine uses the host OS kernel but isolates processes, file systems, and networks. 3. Running containers. When you run a container, the engine creates an instance of the image. Containers are lightweight because they don't require a full OS, unlike VMs. 4. Container registry. Images are stored in repositories called registries, e.g., Docker Hub, Amazon ECR. Developers can pull images from these registries to deploy them. Key components of containerization include 1. Docker file. A text file that defines how to build a container image, e.g., application code, dependencies. 2. Container image. Built from the Docker file. It serves as a template for running containers. 3. Container engine. Manages containers, starting and stopping them, e.g., Docker containered. 4. Orchestration tools. Tools like Kubernetes manage multiple containers, handling scaling, load balancing, and recovery. Benefits of containerization include 1. Portability. Containers run consistently across different environments. 2. Efficiency. Containers are lightweight and start quickly. 3. Isolation. Applications are isolated, avoiding conflicts between dependencies. 4. Scalability. Easily scale applications using orchestration tools like Kubernetes. 5. DevOps friendly. Simplifies CI/CD, continuous integration/continuous deployment, pipelines. Thanks for watching. For more tech interview materials, please go to our website at bowz8.com.